Our session today has to do with pulsating stars. So I'm really looking forward to see what's new, what's exciting, what's cool, what's happening when it comes to the world of pulsating stars. I would like to remind all of you who have a presentation, even those who don't have a presentation here, but you're doing research on something, to consider submitting your work at the Journal of the AAVS. It's free of charge for all of you. It's one of the member privileges, and it is a peer-reviewed journal, so your work will be there for posterity and for everybody else to use your results for their own research. So I would like to really encourage that. And with that, I would like to introduce our morning's keynote speaker, Professor Leanne Wilson. Professor Wilson is from Iowa State University, and she's going to talk about Miras, mass loss, and the ultimate fate of the Earth.
Thank you, Scylla, for debugging the system for me. So I'm going to tell you a story, and these three elements are all part of the story: Miras, mass loss, and the ultimate fate of the Earth. We'll start by reviewing the basics about Miras. Many of you know this. Miras are cool giants, which means that their surface temperatures are around 3,000 kelvins. Their size is about the size of Earth's orbit at 200 solar radii, and their luminosity is 3,000 to 5,000 times the luminosity of the sun. These are big creatures. They are also, and this is important for this context, pulsating stars with periods around a year and large visual amplitudes. It's a requirement. If you want to be a Mira, you have to have a visual amplitude of at least 2.5 magnitudes, and they range upward from there. One of my favorites is Chi Cygni, with an amplitude of nearly 10 magnitudes, as you can see here. A period of about 408 days, and it demonstrates features that are common among Miras, that the maxima are not always at the same height, and that there may be features like bumps on the rising or falling branch that come and go from cycle to cycle. So they don't repeat regularly like clockwork, but they have variations that are interesting and worth monitoring. Here, thanks to AAVSO members and some people who even started observing these before AAVSO existed, we have 100 or more years of many of the Miras. Here are 40 years picked out of the Chi Cygni light curve. Again, you can see some of the kinds of, some of the variations in the brightness of the maximum and some of these features that come and go and move around on the rising branch of the light curve. These stars also have emission lines, and that turns out to be very important for understanding what they're doing, and they have infrared excesses. They don't have emission lines all the time, but they have emission lines during part of the cycle. And this is important for several reasons. First of all, anytime a star has emission lines, something funny is going on. It's not a simple static star that's sitting there, because then the temperature decreases as you go outward, and as you get into parts of the spectrum that are more opaque, that is to say lines, you're looking at cooler material and you get absorption lines. So absorption lines are normal, emission lines are not. There are only two ways to get emission lines in a star: either an extended atmosphere, so that a lot of what you're looking at is hot gas in front of cold space, or a temperature that increases at some point going outward, which means something has to be heating it above what you would otherwise expect. Well, in this case, we have a pretty good clue as to why that might be the case, because these are pulsating stars. And pulsating stars get shock waves from the pulsation that form in the atmosphere. The shocks do several things. They expand the atmosphere. They push material farther out, so the atmosphere becomes much higher and thicker. And they also compress and heat the gas, which gives you a couple of opportunities here for emission lines. Also, in a perhaps counterintuitive way, they can produce regions of the atmosphere that are cooler than you would expect. And I can illustrate this here with some curves from a model using the Bowen code. What we see in this plot is, oops, I keep doing that. This is the pointer. Okay. What we see, oops, one more. See here is 4 different phases in the pulsation cycle: radius this way, temperature this way. Now, deep in the atmosphere, when a shock wave comes through, it compresses the gas The gas radiates efficiently and cools back down towards the temperature that it should have, which is the radiative equilibrium temperature that's represented by these dashed lines. As you get a little farther out in the atmosphere, when the shock comes through and compresses the gas, it radiates efficiently. But then it expands between the shocks. It becomes lower density. It does not radiate, or it does not interact with the radiation field as effectively, and it can end up being supercooled. And so we have this region here about 2 stellar radii where the model suggests that the gas temperature is lower than you would expect in a static atmosphere. And that's exactly where you need to have a low temperature to get the dust forming. You also need extra density there, which you get from the expansion of the atmosphere that's brought about by the pulsation. So you have a refrigerated zone. It's just like your refrigerator. You compress the coolant, let the radiation take away the and convection take away the heat, then you expand it, it cools, and you let the interior of your refrigerator get cool. Here's another picture of the same kind of model. This is showing the radius this way and time this way. The model starts with a very smoothly varying little piston boundary condition, but then as you get through the photosphere, which is this dark line, the part where you can see the atmosphere is above the photosphere, then you start developing shock waves. You develop one major shock that goes all the way out through the atmosphere, and that's the one that you saw in the previous slide. And then in almost every case, you develop a little secondary shock that has to do with the ability of the atmosphere to transfer waves of different frequencies. The pulsation period in these stars is a little too long, and it gets essentially broken up in the deeper atmosphere. The refrigeration zone I was mentioning, so compression in the shock, the lines are close together, it's high density. Expansion between the shocks, the lines get farther apart, lower density. The cooling, and this is the region where you expect dust to form. Just for scale, this is the Earth's orbit. This is the orbit of Mars. We're talking about something that fills up the inner solar system in the case of a Mira variable. Now, Miras also have infrared excesses indicative of dust. When I first started studying Miras in the early 70s, we did not know whether Miras were losing mass. As you're going to see as we come along here, that turns out to be almost a defining characteristic of the Miras. But we needed infrared observations, and we needed space observations to really tease out what was going on in these stars. Almost every Mira has an infrared excess of some amount. To get dust forming, we need a couple of things. We need a low temperature, below 1400 or even lower than that, and we need an extended atmosphere with a density that's higher than in a static atmosphere. In a static atmosphere, by the time you got to this temperature or below, you'd be so far out there'd be nothing there to make dust from. So you need the stuff to be out there, and you need it to be cold. Once you have dust, magic happens, because the dust is very opaque to starlight. It absorbs or reflects the starlight. It picks up momentum from that process. It gets pushed out from the star. It interacts with the gas and drags the gas along, and voila, you have mass loss. So once you can have dust, all sorts of fun stuff happens. And putting it together, the pulsation extends the atmosphere and produces a refrigerated zone. Starlight pushes the dust drags the gas, and you have a process of mass loss that's what kills most stars. Stars from about 0.8 to 8 solar masses lose their envelopes from this process and end up as white dwarf stars. We have some funny arguments in the field of people doing models for this. Some of us call this dust-enhanced pulsation-driven mass loss, and some of us call it pulsation-enhanced dust-driven mass loss. The bottom line is you need both. You can't get it without having both of those processes present. All right, so now let's put this in the context of the evolution of stars like the Sun. Here's a classic plot of the evolution of the Sun taken from Boothroyd, Sackman, and Kramer paper in '93. And the formation of the Sun, the main sequence of the Sun, which is where you have hydrogen fusing to helium in the core. It's a great fuel. It produces lots of energy, and it's a very slow reaction. So we have time to evolve and come and become members of the AAVSO. Then at some point, about 5 or 6 billion years from now, the core will run out of hydrogen, and we'll move on to the next stage. The core will shrink down into a very dense, degenerate body about the size of the Earth. The rest of the star will expand to become a red giant. It will continue to use hydrogen as its main source of fuel, but now in a little shell around that degenerate core. And as it produces more helium, the helium gets deposited on the core grows. And so the core grows from about a tenth of a solar mass here to about a half a solar mass up here. When the core gets to be about a half a solar mass, it is able to start fusing helium to make carbon and oxygen. And this takes place in a fairly abrupt process called the helium core flash that until relatively recently wasn't even included in models, but you simply took a model here and you said, oh, helium core flash, restructure it, make a stable model, start over down here. Now there are some codes that can actually follow that process, but that wasn't true until relatively recently. That's why there's a gap in this plot. It's an old picture. Then we have a kind of second main sequence where we're converting helium to carbon and oxygen. And the carbon and helium can make, so the three heliums get together to make a carbon, and the carbon and helium make oxygen. And this is a decent fuel, and the luminosity is only around 100 times the current luminosity of the sun. So this is a fairly long-lived stage. And then once the core is entirely carbon and oxygen, you get the same thing that happened before. The core shrinks, the rest expands. We move up the giant branch again asymptotically, so we call these the asymptotic giant branch stars. And when enough helium builds up around the core, then we have a helium shell flash, a change from converting hydrogen to helium to converting helium to carbon and oxygen. And the little wiggles back and forth here are meant to represent the 100,000-year cycle of helium core flashes, not the pulsation of a Mira variable, but it is also up in this part of the evolution of the star that it becomes a Mira variable, one of our pulsating stars. We know that some of them, we're pretty sure that some of the Miras actually do experience flashes, and we think we have some observational evidence for that. In fact, thanks to these long-term light curves from organizations, organizations like the AVSO. Years ago, Matt Templeton and I, working with some material that Jan Amati had left, looked at a large number of long-term light curves from Miras, and this is a plot from that paper showing behavior of T Ursa minoris, roughly constant period, and then something happened, and the period began to decrease. And that's consistent with, well, let's see, before we do that, so this is the light curve over the same sort of period of actually going up to today. And you can see that this looks like a nice big amplitude Mira, and the period is shorter and the amplitude is smaller in recent times. In fact, comparing an early epoch few years with a later few years, this is the most recent 2,000 days, and this is back towards the beginning. It looks like a different star. It has really, really changed. And this is actually consistent with the kind of behavior we expect in the shell flash cycle as it starts. So perfectly fine luminosity radius and therefore pulsation period, and then a dip. We also have some other stars that that we think have been caught in a little later, slower part of the shell flash cycle. This is from a paper by Wood and Zaro from 1981, where they compared the period changes in R. aquila, R. hydrae, and W. draconis with some then models of shell flash behavior, and found that it seemed pretty consistent. A more recent reanalysis of the R. hydrae data is in Zylstra et al. 2002, where they looked not only into the changes in period, but into other observations, including variations in the mass loss rate, a very interesting analysis in that paper. Well, okay, mass loss. We've sort of segued from Miras into mass loss, so now let's talk a little more about mass loss. Back when I was in graduate school in the Dark Ages, we knew that stars had to lose mass at some point. We knew that if stars below 1.4 solar masses didn't lose mass, they'd end up as white dwarfs with masses almost exactly equal to what they started with. And stars that started out with more mass than that would all explode as supernovae. And we were quite sure that didn't happen for two reasons. One of them being that most white dwarfs have masses considerably lower than that. In fact, stars that have had time in the age of the universe to evolve off the main sequence have to have masses 0.8 or bigger, and most of the white dwarfs are smaller. So you know stars losing mass somewhere in their evolution. And you also know you aren't getting supernovae, and this is a mapping of the initial mass to the final mass. It's a fairly tough job to do that mapping because you have to find and observe and get masses for white dwarfs in systems where you have another star or other stars to tell you the age of the system, so you can get some idea of the progenitor. So these are binary systems and some clusters that have been used to get these initial final masses, and you can see at the high end the error bars in initial mass are fairly large. But in any case, what you see is that almost all the stars are below 1.1. Most are below 1 solar mass, even with progenitors up to 4, 5, 6, and 7 solar masses. So we now believe that stars up to solar masses in present-day populations are ending up as white dwarfs and not as exploding stars. So where does this mass loss happen? Well, let's start by looking at our sun right now. It's losing mass, but not a whole lot. The solar wind is about 3 times 10 to the minus 14 solar masses a year, and gradually decreasing as the convection zone of the sun spins down. And that only is going to take off a tiny amount of mass. And E equals mc squared and fusion reactions are also removing mass from the sun, sending it out as starlight. And that's of the same order of magnitude, about twice as much. And that is actually increasing because the luminosity of the sun is increasing slowly over time. But you put those two together and you're still talking about less than 1% of the mass of the sun coming off over the whole main sequence evolution. And so that's not going to solve the problem of how to get all those white dwarfs. What does help for mass loss, the things you want to make it easy to get mass off of stars, you want low gravity, you want a big star, you want high luminosity, lots of power to work with, you want pulsation because that elevates the atmosphere and pushes it out, and you want dust because that removes the material from the star. Finally, and of course, I just described our Miras. So how important are Miras in the mass loss process? Well, this is where mass loss happens. This is where the Miras are. People realizing back even in the 70s that we needed to find a way to include mass loss in stellar evolution calculations, tried to use observations to get some sort of a handle on how the mass loss proceeds. And one of the early and most widely used such relation is the Reimers relation. He took the first couple dozen stars with reliable mass loss rates among the M giants, and he fitted them to a relationship 4 times 10 to the minus 14 LR over M, where these are in solar units, solar masses a year. And this is pretty close to matching the sun, as well as all those red giants. So it looked like it could be a universal magic formula for putting mass loss into evolution. So people immediately ran and put this into a lot of evolutionary codes and tried to reproduce what's seen in globular clusters, where some of the Lyrae stars are stars that have lost mass, and what's happened in other populations. And they fairly quickly found that that one universal formula with that one single constant up front didn't actually solve all the problems. So they added a little pre-parameter so that they could adjust it and see what would work in different situations. And they got more situations to work, but not all of them, because it became quite clear that at the end, the mass loss rate has to be changing much faster than it would be with just this kind of dependence. Meantime, and there's been a number of different empirical relations with different fits, but they all tend to have some of the same problem. Meanwhile, from 1978 until now, it's been possible to do some kind of modeling in for the atmospheres and mass loss process of Miras. And there's been several groups working, including our group at Iowa State for a long time. And what the models tend to find is that there's a much steeper dependence of mass loss rate on stellar parameters than most of the empirical relations find. So models are saying it's steep, observations are saying it's gentle, but except that doesn't always work. And we found a way to compare a lot of different formulae and models by taking an evolutionary track, which tells us what radius goes with what luminosity. So this big LR becomes L to the 1.68. And then that allows us to follow the evolution of stars in different systems with a power law fit in the part of the evolutionary track that's interesting. So we have an exponent for the luminosity and an exponent for the mass that tells us how the mass loss rate varies. And in our models, we tend to get those exponents up around 10 to 20. Not 1.68 and 1, but 10 to 20. So a big difference in how fast the mass loss rate evolves. When you have that kind of a steep dependence, this is the kind of picture you get for the evolution when you look at how the mass changes with luminosity, which is a proxy for time. The luminosity is increasing exponentially as you evolve up the AGP. So log L and time are really the same kind of scale. So here we have a star that comes in, more or less constant mass until it gets near this pink line, which I call the death line. I'll explain that in a minute. And then it turns a corner, and then it crashes down to form a white dwarf. And in the particular models that we used here, the luminosity depends a little bit on the total mass, so this isn't going back in time, this is just sticking at constant core mass. The nuclear reactions don't have any time here to build up more core mass because it's going so fast. So all the interesting stuff is happening right here around the death line. Come in, turn the corner, and crash. And around that death line is a zone I call the death zone, which kind of shows where the mass is going, where it's going from constant mass evolution to constant core mass evolution. And this is one order of magnitude either side of the death line. And you can see that it really does contain most of the information. Now with the Reimers relation, the death zone is like from here to here, and this picture doesn't work very well. But with a steep mass loss formula, it works very, very well. So the death line is where the rate of change of the luminosity equals the rate of change of the mass. So where both of them are changing equally. On the one side of it, the luminosity change dominates. On the other side, the mass change dominates. And so you can write that from evolutionary models. You can get 1 over LD LDT, and what you end up with is that the mass loss rate of 10 to the minus 6 times the mass of the star, solar masses per year, that's the magic number. That's where you kill stars. It's right around that mass loss rate. For less than a tenth that mass loss rate, the mass is changing very slowly. The mass loss rate is low, and it's also low mass loss rates are always harder to see. For greater than 10 times that, the star dies quickly, and plus it's probably invisible behind a cloud of its own mass. So most of the mass-losing stars that you start observing are going to be the ones near the critical mass loss rate. And that turns out to be the Miras. This is the death line plotted on a observed period luminosity relation for Miras, and it seems like a pretty good fit. So Miras are stars in the death zone. I would even say Miras are the stars in the death zone. And this helps us explain why the empirical relations are so different from what you get from the models, because when you have a selection for stars in the death zone, then you end up with, and you can't easily measure precisely the luminosity, the radius, or the mass of the stars you're observing. What you end up doing is reproducing the selection of the stars that are losing mass rather than reproducing how a particular star does it. So based on the models, we have stars evolving like this, and then as they start losing mass, they veer off. And if we throw the Reimers relation on it, it matches the death line perfectly. That's true of most other empirical relationships derived in the same way by taking observed mass loss rates and plotting them against stellar parameters. They do a really good job of finding the death line. They tell us which stars are losing mass. They don't tell us how a star will lose mass. They tell us which stars are losing mass. So they're useful, but they're not useful in the way that they've mostly been used. One exception to this is the Vasiliadis and Wood relationship for Miras especially, plotting mass loss rate versus period. Why is this different? Well, as I said, the luminosity, radius, and mass are hard to pin down. 10% is a really good accuracy on the luminosity, radius, or mass for one of these stars. But you guys know how well you can pin down the period. 1% is pretty easy to get with the kind of light curves we have for these stars through the AVSO. 1% is very easy indeed. And that means that any steep dependence of the mass loss rate on stellar properties can be seen in this plot, and you get a very steep dependence of mass loss rate on period, which means radius, luminosity, and all that. And it is also, I like to use this plot to show that the Mira mass loss rates, the observed mass loss rates for Miras, are in fact exactly those you expect for the death zone for stars from 0.8 to a few solar masses. So Miras are in the death zone. Miras are probably the stars in the death zone. And the dependence of mass loss rate on stellar parameters is probably much steeper than most people have assumed. Beyond the death zone, we have another area of stars that are losing mass very quickly. If we look here, there's kind of a saturation at 10 to minus 4 solar masses a year. And so I didn't actually extend those lines beyond 10 to minus 4. The models don't do very well beyond that anyway. But probably they even out at about that rate, which is already fast enough to have them evolving at more or less constant core mass. So those are the OHIR stars that are hiding behind their own garbage. You can only detect them in the infrared or radio. All right, so now let's change course a little. I retired, so I can play with stuff that isn't fundable, so I'm going to have some fun now. And I'm going to ask the question of what happens to the planets when all this is going on. Again, we have the evolution of the sun. And it's pretty simple to get some answers anyway. We can look at the energy balance for the planets, and we can write it in a fairly simple way. We have the power that is absorbed by the Earth. All parts of the Earth, the atmosphere, the oceans, the land, everything can be described in terms of the geometric cross-section of the Earth divided by 4 pi d squared. So that's the geometric fraction of the sunlight we absorb. There's the sun's luminosity. And then there's this little factor 1 minus A, where A is the albedo. Albedo tells us how many of these little things bounce off, and so how much of the sunlight that hits the Earth gets bounced off and doesn't heat us up. Then we can look at the power out, and this is the simplest formulation of that. It depends on the total area of the Earth. There's some kind of representative temperature for the Earth as a whole, and then there's something called the emissivity, which tells us how efficiently the Earth radiates back into space. And the cool thing about this simple approach is all the hard stuff's in there. Lots of physics hiding in that. The composition of the atmosphere, the nature of the surface, all kinds of stuff is hiding in there. But we can be clever. Here's the energy balance. The radius of the Earth factor appears on both sides, so get rid of it. And then group things. Here's what I like to call the albedo factor. 1 minus the visual albedo over the infrared emissivity. Here's the geometric factor with luminosity, and that's the solar constant, which is now about 341 watts per meter squared, going up. And the albedo factor here is hard to compute. Man, that is really tough to compute. If you want to predict the temperature of a planet by computing the albedo factor, that's a tough job. It takes a lot of people, big computers, and a lot of information. But if you've got an idea of what the temperature is, and you know L over 4 pi d squared, you can get an idea of that factor. And it's about 1.1 for the Earth at this point. Okay. So we can turn it around and use the stuff that's easier to measure to derive the hard-to-measure factor. It's not predictive, but it's still useful. Well, then I want to actually follow the evolution of the sun. I'm going to be a little bit even more approximate. So here's the whole formula. T planet compared to the Earth's planet temperature now. So all the planets can be studied this way. Albedo factor, luminosity of the sun, and the distance. Now, solar mass loss could change the distance, and it probably will, but only very late in the sun's evolution. So I'm going to follow this initially with no solar mass loss, constant distance. The albedo factor will probably change, and it is different from planet to planet. but it's different by modest amounts compared to what the luminosity is going to do. So I'm going to take a first approximation, ignore that as well. And when I do that, then the only thing I really need to know is the luminosity of the sun, get an estimate for how hot the planets are. So here's the luminosity of the sun plotted not logarithmically but linearly. And so the main sequence is hiding down here. And then we have the red giant branch and the AGB. The AGB actually goes farther up. The models I used to make this plot didn't track it once it went into shell flashing. Let's blow up the main sequence part. So here's the sun now. And by the end of the main sequence, the sun's going to be about twice as bright as it is now. So what happens to the temperatures of the planets when that goes? Well, here we have the temperature versus luminosity. So time is going this way, slowly. We have the habitable zone here in green. We have the Earth now. Earth is going to leave the habitable zone when the sun is about 10% brighter than it is now and end up being too hot. Mars will enter the habitable zone just about the time the sun leaves the main sequence. So the habitable zone will migrate from Earth to Mars over the next 5 to 6 billion years. And here's a recent model studying what happens as the Earth leaves the habitable zone, as it goes from being a pleasant place to be to being very, very unpleasant indeed. Present solar constant, 341 watts per meter squared, not quite 10% higher at 371 watts per meter squared, and we're getting close to boiling all the oceans. And then 380 watts per meter squared, and we're talking a furnace. So it's a fairly abrupt, unpleasant change looking for us in about 1 billion years. Well, let's put that aside for now and just worry about the survival of the rocks and hard stuff on the Earth that takes a little harder to destroy. And let's look at the giant phases. So this is the beginning of the RGB, and it's an exponential rise in luminosity to the tip. And then it's an abrupt change at the helium core flash. It's a nice sort of second main sequence here as it converts helium to carbon and oxygen, and then we go up the AGB. And here I've extended that to where we know the stars get to before mass loss kills them off. And during that evolution, again plotting temperature versus luminosity, but the luminosity is going to go up to somewhere in here. We have Earth leaving the habitable zone, Mars passing through it, Jupiter passing, Saturn passing, Uranus, Neptune, and by the time we get to the tip of the first red giant branch, the habitable zone will be out in the Kuiper belt. Okay? All of the planets, as we legally call them now planets, the 8 planets, will be too hot for comfort on this simple model. When we then have the quiescent helium burning phase, the clump giant phase, we will actually have some nice habitable giant planet moons. So if you can survive that first giant branch or come back for a visit, that's a good time. And then when it gets to the top of the AGB, we again have the habitable zone out there in the Kuiper belt somewhere. How hot will it be when we reach the maximum luminosity? Well, this is a model that suggests it'll be about 2400 K on Earth, and that's enough to produce magma oceans with little floaters in them and an atmosphere that's full of rocky stuff. Not a very pleasant place to be. It's considerably hotter than most potter's kilns or present-day volcanic lava. So that's a hot place indeed. A very melted planet. Well, given that it melts, does it survive anyway, or does it end up inside the sun? This turns out to be back circling around to the mass loss question, because the distance between the Earth and the sun will increase if the mass of the sun decreases. This eventually happens via mass loss. But the fate of the Earth, whether it ends up inside the sun or not, depends critically on when and how that mass loss happens. So without any mass loss pre-AGB, as the sun moves up the AGB and expands out towards the orbit of the Earth. This is the Earth in its present orbit, comes in. Eventually here, this is the end of the first giant branch. Venus has had it. Mercury had it a long time ago. Venus is dead. Here comes the Earth. It finds a part of the atmosphere of the sun where the density is high enough for gas drag, and there may also be some losses due to tidal drag at this point, and it spirals into the sun. Okay, so if the sun ends up ascending the red giant branch, the asymptotic giant branch with its original mass intact, the Earth ends up inside the sun. Mars, on the other hand, just barely gets away. Just when it's beginning to feel drag, the sun enters the death zone, which is here, and Mars gets away. So Earth doesn't, Mars does. But looking back at this, the difference between the peak luminosity on the red giant branch and the AGB is not so huge that the red giant branch couldn't, in principle, make it into the death zone. There is a tricky bit there, which is that if we do have a high sensitivity, luminosity, and radius, then it tends to be the case that either you lose everything or nothing. It tends to be hard to lose only a little bit because you'd have to have your parameters so fine-tuned that the core flash happens just after you enter the death zone before you lose all that mass. So that would tend to say that either you lose it all or you end up going up the AGB with more or less what you started with, but there is a caveat. It may be mass loss associated with the helium core flash. We don't really know that for two reasons. Model-wise, I don't think anyone has calculated models that trace mass loss evolution through a helium core flash to see how the relatively rapidly changing stellar parameters influence the process. And second of all, there is not a single star out there we can point to and say, oh yeah, that one, it's going through the helium core flash. We'd expect of the clump giants out there, we might expect to find remnant mass loss around about 1 in 10 to the 4. And there's plenty of other things that can produce remnant mass and other things around those. So we don't have observations and we don't have theory at this point to tell us, but based on fitting things like the period luminosity relation and so on, I'm pretty confident that the answer is in the range of 0.8 to 1 solar mass for our sun. And that turns out to be quite interesting because 0.8 is like just exactly enough to get away. If we end up ascending the AGB with 0.8 solar masses, then the Earth does what Mars did in the other one. It's feeling gas drag, but the sun is beginning to lose mass, and the result is that the Earth gets away. So that's what it takes, and it all has to do with Miras and mass loss. Well, then we might ask the question, can Earth stay habitable longer? And, you know, the universe might help us out here by sending another star to pick up the Earth. Some simulations of many examples suggested that there's about 1 chance in 2 million that a passing star system could capture the Earth into a habitable orbit and take us along in the next billion years. So if you like to rely on the lottery for your income, this is a good option. Otherwise, we might be looking for another option. Can we do something? Can we make changes that would make the Earth stay habitable longer? Well, an important factor is this albedo factor. An important part of this is the atmospheric concentration of CO2. So maybe we could tune the carbon dioxide content of the atmosphere to stay cool longer. Right? We could just keep decreasing the carbon dioxide and keep the Earth cool. It turns out that that doesn't actually work very well because by the time we get to 1.1, the amount of carbon dioxide that we would need to have for Earth to be cool is too low for plants. So we lose photosynthesis. And in fact, most of these models that predict the end of the habitable Earth around here have already reduced the CO2 to as much as can possibly be done. So that is not going to help us very much. What will really help us is to somehow find a way to stay in the habitable zone by moving ourselves out towards the orbit of Mars over the next 5 or 6 billion years in some way. And one way of doing that might be to persuade the sun to lose mass. And this is pretty far-fetched, but okay. We'd have to get a factor of 100 or more increased. This would probably also extend the main sequence lifetime, since the action in the solar wind has to do with convection zone spinning. If we could spin up the convection zone, we might be able to. If you hit the convection zone with a Jupiter aimed precisely, you might actually be able to do this, but that would mess up the inner solar system, so I don't recommend that approach. So maybe we can do something much simpler and move the Earth. We would need to increase its period by about 1 second every 150 years to stay in the habitable zone until the end of the main sequence. 1 second in 150 years. That's a tiny amount, isn't it? Can we do that? Well, we know how to do that in principle, which is we fly something smaller by it, and it gets a little bit of exchange of angular momentum, and it moves into a slightly bigger orbit, and you do it many times, and you can move it. There is actually, kick it once, it's no good because it will come back to where the kick happened, and you'll still get cooked. But you do it many times, and you can get it to gradually move outward. And there is actually a body out there, Curinia, that's in an orbit that's very nice. It exchanges momentum with the Earth once every few hundred years, changes its period, changes the Earth's period slightly, and moves back and forth, exchanging momentum with it. It changes, however, by not quite enough. It's about 4 orders of magnitude too little, even with repeat encounters. Changes its own period by about 2 days. It's about a 5-kilometer, 10 to the 14 kilogram object, so something that's much bigger, like 10 to the 19th kilogram or 250 kilometers. If we could put that in that orbit, we might be able to use that. Where would we get that from? Well, Kuiper Belt, asteroid belt, moon of a Jovian planet. It's right at about the border between things that are round and things that aren't round, so it's a pretty big object, but there's a lot of those out there, especially in the Kuiper Belt. The problem is we need to steal angular momentum from somewhere, because we need angular momentum about as much, 84%. We'd have to increase our angular momentum by about 84%, and either Jupiter or Venus plus Mercury together are the only real sources of that angular momentum. We have to send our little body to steal angular momentum, give it to us, steal some more, give it to us, steal some more, give it to us over time. Koryaksky, Laughlin, and Adams proposed using the Kuiper Belt object to do this. They got the same mass estimate we did of 10 to the 19th kilograms. Jupiter would have to move inward by about 0.03 AU, which doesn't sound like much until you start looking at the question of the stability of the solar system. And if you even just move Earth by a little bit, you encounter a chance of destabilizing the inner solar system, never mind Jupiter, which dominates the whole picture. So moving Jupiter may not be so good, but maybe we could move Mercury and Venus. So on a scale of big projects, I would put this one in the middle between terraforming Mars and making a Dyson sphere. I seem to be running out of time, so I'm not going to get into details there. People describe advanced civilizations in terms of Kardashev levels. The Earth today is using about 10 to the 15 watts from a combination of solar power, nuclear, and fossil fuels. The solar power includes direct solar, wind, hydropower, and so on. 10 orders of magnitude, 1 order of magnitude higher than that would be capturing all the light that hits the planet from the sun. It's a Kardashev 1. Moving the Earth is an order of magnitude above that. Capturing all the light emitted by the sun, a Dyson sphere is 9 orders of magnitude above that. And capturing all the light in the galaxy, well. So could we do it? Could we do this? One of the really hard things is the commitment involved. It's a 5 billion year project. We have a little trouble with things that exceed 4 years. The number of civilizations in our galaxy we might talk to is the number of stars in our galaxy times this fraction of the average number of habitable planets, a fraction of those that make life, the fraction that makes civilizations, the longevity of the civilization of the age of the galaxy. Even if you take this set of 3 things to 1, it still turns out that only if you have a billion-year longevity for civilizations is there a chance of having someone out there to talk to, and that's the same condition we need to be able to move the Earth, is a billion-year, multi-billion-year commitment. So this is now my review of what I said. Miras are in the death zone. The Earth is likely to end up inside the sun. A planet where Mars is now is likely to escape. Earth will leave the habitable zone in about 1 billion years. It will move out. The habitable zone will move out to Mars, and then out to the Kuiper Belt. And to extend habitability, we might be able to alter the albedo factor. I didn't discuss altering the A part of that. That's a lot of fun too. And increasing the distance might be achievable if we can commit ourselves to small changes proceeding over a long time. And there we are.
Thank you, Liam. I guess the encouraging part is that we have 1 billion years to figure it out, right?
We should get started sometime in the next half billion years if we can, but yeah, we don't have to start.
So any ideas are very welcome. Any question?
So, Leanne, thank you for a very depressing talk. We have 850 million years till we leave the habitable zone, more or less. And then we have a big gap before Mars gets into the habitable zone. Isn't that the real problem, is that gap between 850 and... So isn't it more important to try and move Mars closer so we can jump ship quickly?
Well, we could do that. It's easier to heat stuff up than it is to cool it down. So I tend to figure we can manage to inhabit Mars well before we have this problem gets critical. But if we like to preserve the big one, Earth, then we need to move it out that direction. Now, what happens when we get close to Mars? I didn't even start thinking about that. A lot of interesting problems to solve. Not very fundable, but I'm retired, right?
My suggestion for your retirement is to write a sci-fi novel to incorporate all of this. My question is, what's the composition of the mass that's being lost?
It's pretty much, thank you, that's an excellent question, and it's pretty much the original composition of the star. It's material that has not been nuclearly processed, with one exception, and that is in the carbon stars, there has been, the material in the envelope has been contaminated by material that has been processed so that the carbon exceeds the oxygen. But it's still hydrogen-rich material.
How do you measure the mass loss that you're using, and then when you have that, and you have to, then are you getting the exponents by the model? In other words, how fast the mass loss comes off your A and your B?
Yeah, the exponents A and B that I showed you are for models. What you need is a velocity and a density and a particular position in the atmosphere. And so in the models you have that, and you just have to average over the cycle. In a real star, you get that by looking at certain lines that are formed and figure out where they're formed, and you can measure the velocity in those lines, and you can learn something about the density there to get your mass loss rate. Once you've done that for a number of stars that also have infrared excesses, you can find ways to calibrate and fit models that just use the infrared excess. So we have a modest number of stars for which that detail process has happened, and a large number of stars for which we derive it from infrared excesses.
More questions?
And when you look at the trail behind Mira, does that give you any way of comparing the model with the reality?
That probably has to do with interaction with the interstellar medium, which means it does contain information about the mass loss process. I haven't looked at that in detail, in part because the kinds of things that we're studying, we tend to be very spherically symmetric and stay in close to the star. But yeah, in the kinds of things that you get with Mira and some of the others, that there's an interaction with the interstellar medium, you can look at the properties of the interstellar medium and the properties of the wind and the properties of the interaction and get some information that way.
The change in period of T years to Miras has been pretty dramatic for observers, and still looked like it was going down. If it's really a shell flash, how much longer do we watch before the next dramatic alteration in its behavior?
Well, that depends on its core mass. Different models with different core mass have different depths and rates of change. So I'd have to look at some current models to be able to tell you an answer to that. I don't know the answer to that, but it's obviously important to keep watching it.
Have you looked at how much Earth warming there is in the 20?
Have you looked at how much Earth warming global warming there is in a 20 to 50 year time frame from this effect?
Minimal, really minimal. Yeah. Big changes in Earth's climate now come from a change in the albedo factor, especially the emissivity, which is changing noticeably. It's not from the solar constant. It's going to take, if you figure it's 1 billion years to change by 10%. That's pretty slow.
Leanne, how well defined do you think the tip of the red giant branch is? So would you like to comment on its use as a distance indicator?
Well, the red giant branch by itself is almost vertical near its red diagram, which means a small error in the location this way is a big error in the distance. But the clump giants tend to have a fairly well-defined luminosity. They sit at one luminosity for a long time. It's fairly well established from models what that should be, and you can observe it in clusters. So using the clump giants as a distance indicator is actually a well-developed process. But the red giant branch itself, it's just too vertical for use for that way.
More questions?